answer for this question. It said here, what if the velocity was to increase by double or 2 times the value? That means if I was to come back over here and I was to say P equals mass is the same, velocity now is doubled to 80. That's what they're asking me over here. Okay, so let's go ahead and do the math, multiply those two numbers together. When I did this at 8 this morning, double check my answer. I got 40,000 kilograms times meters per second. Or let's say this was a quiz and they used words instead of numbers. We could say that the velocity, what was to happen to the car's new momentum if the velocity was to double? The momentum doubled or increase by 2 times the amount. So either way, whether it's in number values or whether it's in words, I did it mathematically so that way I can see 20,000 was my original number, 40,000 is my new number, right? Or it doubled or increased by 2 times the amount. Now on part B, it says here, well, what if the mass was to double? Like, mass shouldn't double, mass shouldn't get small. The conservation of mass says that it should stay the same, but what if this object was to increase the mass by 2 times the amount? Like, what if you were to put a big load of something, it was to carry a heavy object? Okay, well, for that situation, I need to stop for a moment. Am I going to use my original velocity of 40, or am I going to use this new velocity of 80? If I want to see what happens to the momentum, I should probably come back and let's use the original. And that's the reason why I wanted to help us out, to make sure we're all on the same page. Let's go with this original right here. I'm just going to underline it. I'm going to say if the mass was to double, and this mass is 500, so now let's say if we have 1,000 and I multiply it by 40, because I already know what the answer is. If I use 500 and multiply it by 40, I get 20,000. So let's go ahead and let's compare it to the original, multiply those numbers together. 40,000 kilograms times meters per second. There you go. So I can see that if I went with the original, my answer would be 20,000. If I doubled the mass, I can see that my momentum doubles just like over here, or I can say the momentum doubled or increased by 2 times the amount. Alrighty, so I just wanted to make sure I started homework number 2 with us. You have 2 problems, so I did half of it for you. It's not due until Thursday. I'm moving it out of the way. There we go. And I'm going to get our notes out. Alrighty. Notes look like this. Okay, so here we go. We start off with the word momentum. Again, this is a pretty small unit for us. We've got a couple of labs to do with this. We also have a couple of projects that we're going to work with. Think about your projects with 2 other people, or do it in groups of 2, or do it by yourself, your choice. Just keep that in mind. And we do have a momentum lab that we will do in class that we need to partner up with somebody here in class. Momentum can only occur if an object's moving. Can an object have 0 momentum? Sure could. What if it's not moving? It has 0 momentum. So 0 would be a perfectly good value to have as your momentum number. The next thing I want to say is, let's pause for a moment and let's look at the equation. P equals m times v. Velocity truly is a vector quantity that we learned about last semester. And since velocity is part of the equation, that means truly that P is also, or momentum is a vector quantity. Tossing it out there. So if you see a negative P value, it doesn't mean like you have negative momentum. No, but you're moving in the negative direction. There you go. All right, so I just wanted to make sure I tossed and said that because I didn't say it last week. So P equals M times V. An object can have P or momentum if it has a heavy mass or if it has a fast velocity with it moving. Now we know that an object can move, and we also know, because it's physics, we know that an object can come to a stop. And the only way for an object to come to a stop is if there's a force that's applied to this movement in opposite, right? You're going to try to stop it from moving. You have to apply a force, and it has to happen for a certain amount of time period. We call that impulse. The impulse is the opposite of momentum. Now, the cool thing here is that the SI unit for impulse is the same exact SI unit as we have for momentum, which is a little weird because you would think it would be newtons times seconds. It actually is kilograms times meters per second. And because of that, we are able to know in our minds that we can set momentum equal to impulse mathematical equation. And that's pretty cool for us, because that gets us to the next page of notes, which is impulse equals momentum. Remember, they're opposite of each other. One is moving and one is trying to stop you from moving. Our equation, which is on the formula chart, and I'll show you in just a moment, comes out to J, impulse, equals lowercase p, momentum. Now we can rearrange this and manipulate it how we want it to look. So I can say Ft equals mv, or I can rearrange this to say J equals mv, or I can say Ft equals p. I can manipulate it how I need and how I see fit, okay, which is homework number 2. Now, we already know V is velocity, which is meters per second. M is mass. Oh, wait a minute. What if mass was given to you in pounds? You can still get it to kilograms by dividing by 2.2, as a quick reminder. Okay? It must be in kilograms, not grams, and not pounds. F is force, which is in newtons, and T is time, which needs to be in seconds, not minutes or hours. Okay. All righty. Now with that said, I'm going to pause again, and I'm going to come back, or I'm going to come to the formula chart. Here, energy and momentum. Here is the momentum equation, which is mass times velocity, but the impulse equation, it's a little weird, because they actually have it like combined. You can come over here and say J, cover that up, equals Ft, which is our true impulse equation. J equals Ft, okay, force times time. Also, I want to say this because we're about to have a couple of math problems. It says delta T, as in there was a change in time, meaning what happens with a triangle? You subtract it to find the difference. Okay? Or it's kind of like the equation we have right now that we're looking at. We can say J equals mv, and there's a triangle V, meaning that if there is 2 velocities, you need to, the triangle is telling you to subtract it. Okay? So keep that in mind, because we're going to have a couple of problems like that. And let's make sure we do our subtraction, because it's easy cheesy. We can do that. So, or you can change that and take away the whole J, and you can say Ft equals mv. So it is on the formula chart. I don't want no one to get confused. Let's move that out of the way. Here we go. Jennifer, who has a mass of 50 kilograms, is riding her red sports car with a velocity of 35 meters per second, who suddenly comes to a stop before hitting a deer, trying to avoid hitting this deer. She strikes the airbag. Oh, crap. What happens now? The airbag is deployed. Your car is going to end up not even being in the shop or going totaled. It's ruined. right? So now this stops her body, and it took 0.5 seconds or a half a second to come to a stop. What was the force, question mark F? How much force did her body feel when coming to this stop? Well, I went ahead and wrote the equation, and that's the reason why, or the reason why is because there are 4 variables, M, V, T, and F. When I see 4 variables, my brain needs to go to the impulse momentum equation. So I'm going to go ahead, since it's already written out for us, let's fill this in. 50, 35, F, I don't know, and T is 0.5. Let's go ahead and solve for that F. Divide this side by 0.5, cancel, divide by 0.5, F equals blank newtons. And I know we all know this because none of us are new here in this classroom, but I like to leave the notes like this for you to fill in, or you lose a point when you turn them in on the day of the test. Okay. Now, remember those triangles that I just mentioned earlier. When you see a triangle, you do subtraction. Not bad. So it says here, part 2, question 2 says, imagine that a car that has a mass of 100 kilograms, let me go here, is moving 20 meters per second and then comes to a stop. Oh, so this must be my VI and this must be my VF. The momentum goes from, or PI, initially 2,000, and it goes to 0, meaning PF. There's an initial momentum, there's a final momentum. So the impulse, or the definition of impulse is change in momentum, is 2,000, which is true. I mean, don't we see a change in momentum from 2,000 to 0? Subtract the 2 numbers. The impulse is 2,000 because impulse equals momentum. So this is actually my J number. So if the impulse or change in momentum is 2,000 kilograms times meters per second, let's assume that it took 5 seconds, T, to come to a stop. What is the force on this car? All right. Well, I'm going to be honest. There's more than just 4 variables. But deep down inside, when it comes to PI, PF, or VI, VF, what do we need to do? Even if there was a TI and a TF, we would subtract those numbers and find the difference, just like how it says on that formula. So for here, the difference between 20 and 0 for V is 20. The difference for P between 2,000 and PF of 0, 2,000. Alrighty, so that means I'm back to 4 variables. That means we're going to go back to the J equals P, or we can say FT equals MV. Because we have 4 variables. The force I do not know. The T is 5 seconds, the M is 100, and the V is 20. Okay. Not difficult at all, I promise you. We're going to get to a little bit difficult Friday and the end of Thursday. We're still on the easy stuff, all right? We're starting off with easy pace right now. Let's go ahead and figure out this force. We're going to divide by 5. Divide by 5, F equals blank newtons. Not bad, Miss Munson, I got this. Good, good, good. But what I want to get to is this part. Our whole topic, or talking about this today, which is going to be, you're going to have a very quick setup to do on a Friday, a lab, and a lot of it has to do with what we're talking about today, okay? So it says here, imagine a different scenario, same car, okay? It says here, what is the force on the car if, instead of taking 5 complete seconds to come to a stop, this car comes to a stop in 0.4 seconds, meaning fast. Slam on the brakes. Well, what to the force. Let's go ahead and let's keep those numbers the same. The FTMV, except for the T. We're going to change it now. This is the new T. So we're going to have force. My T is now going to be 0.4. I'm going to leave M and V the same. Divide by T, divide by T. Force equals blank newtons. Hopefully on the first problem you got 400, and on the second one you got 5,000. Okay? So when we look at the actual numbers, mathematically, if I took a longer amount of time to come to a slower stop, there is less force that's exerted to the car. If I slam on the brakes in 0.4 seconds to come to a stop, the force increased to 5,000. It's a big difference, huge difference. So the whole point of today's topic is if I decrease the T, I can mathematically see here that I'm going to increase the F. And we called this last semester inverse. When one goes down, the other goes up. When one goes up, the other goes down. Okay? So it's about safety today. Let's call that. Title of the lesson of the lecture is safety first. Let's call it that. Let's get to cars. Okay, and we're going to call this part right here crumple zones. So cars long time ago, long time ago, were not made by the same material that they're made nowadays. Nowadays, when people say, golly, you got into a wreck, or you got into, what kind of wreck did you get into? And you're like, it wasn't a bad wreck, it was just a little dent. Like, I wasn't even moving fast. But yet your car may have had some major damage, the outside of it, right? And the reason for that is because cars now are built with what we call a crumple zone, okay? So it says here that you can see over here with our car versus this car, not much of a crumple zone at all, you can see. You can see that if we increase, which we can see this right here mathematically, the stopping distance, or how much time it takes to come to a stop, we are going to mathematically decrease the amount of force. Now remember, if we're decreasing the force of the car, we're also decreasing the force on you. And that's the purpose of it, is we don't want people to get hurt or injured, right? Long time ago when I grew up and I was a kid, cars didn't have all of these airbags and side airbags and rear airbags. There was no such thing back then. The cars were also built, made out of metal. They didn't crumple up like they do nowadays. All right, so it says here, this is why modern cars have what we call a crumple zone. This section right here is called the crumple zone section, as well as in the back. They're made on purpose, true, to get crumpled up. Because if it takes longer to come to a stop because of all of the crumpling and damage that's occurring, then we're going to have this crumple zone area of the car is designed to crumple on impact in order to increase the amount of time that it takes to stop. And if we can increase that stopping time, then we can decrease the force on not just the car, but on you as well. Okay? On you as well. That's what the whole purpose of today's lecture is about. Now, not only that, these crumple zones, which didn't exist when I was a kid, Cars now, like I mentioned earlier, now they have all these airbags. There's front airbags, there's passenger airbags. Some of them even have side airbags where the windows are on the side, even the back. Some cars have back passenger airbags nowadays. Like, they're really trying to strive for safety, which is a good thing. That's not a bad thing. It says here, though, airbags are also used with the same concept as a crumple zone, but not necessarily to the car. It's a crumple zone for the person in the car, right? Also, seat belts. We use that to help slow our bodies down. It says here they are going to increase the amount of time it takes for your body to come to a stop on that impact, so we can decrease the amount of force. The problem, though, I will say, is that now, what about your organs? Because if your car is traveling 82 miles an hour, your body, your heart, your organs are also traveling 82 miles an hour, and you don't have a seatbelt on every organ in your body, right? Thank goodness we have a rib cage to hold our heart and our lungs and other things in, but unfortunately, sometimes we still end up with internal injuries because our body was coming to such a strong stop, it still affected our body, our organs, because they were still traveling at whatever speed you were traveling at or the car was traveling. Let's take a glance over here, and then we got a quick 2.5-minute video that we're going to look at, and then we'll finish this page in a little part of the top, and that's it. A good solid hour of lecture today. All right, so let's take a glance over here. I see the mass of a car, it says here, is 100 kilograms, and it shows me that the car is traveling at 50 VI and slows down to the VF. So I have an initial and a final. And remember on those that formula chart, we had a delta where you need to subtract the difference and get that subtraction done. Don't forget to do that in just a moment. If the car took 10 seconds, T, to come to a slowdown, then what is the force on the driver? How much force did your body experience? So for this situation, I'm going to call this step 1, just to remind me that I have a VF and a VI final first. So 20 take away 50 actually comes out to a negative 30. But don't forget, remember, I started off this lecture today talking about, hey, velocity is a vector, and that means momentum is a vector quantity, right? For those of you going into engineering or into university physics, please know that you will have to take that vector into account. But here, I'm going to ignore it because I know that it means direction, all right? So now I'm going to say step 2. Step 2, I have an M, a V, 1V. I have an F and a T, so I'm going to say J equals P, or MV equals FT, right? I broke it down. I just got this and broke this down. I have a mass of 100. Velocity of 30, yes, it's a vector, but I'm going to ignore it. Force of, I don't know, and T of 10. Divide by 10, divide by 10. Force comes out to blank newtons. Not bad. But the whole purpose of today is to get into our minds, because you're going to need this for a quick little lab we're going to have on a Friday, that if I can increase the amount of time on an object that it takes to come to a complete stop, then I can decrease the amount of force to that object, right? We're trying to cut back from concussions and broken bones. It says, let's do this again. We've got a runner who has a mass of 50 kilograms who's traveling and slows down from 10 to 2. The difference in the velocity is going to be 8. I'm going to ignore the vector direction. The force was actually 40 newtons to slow down it took. how much time did it take for this runner to come to a slowdown? Because they didn't stop. Or J equals P, FT equals MV. I'm going to put F, which I actually have this time at 40. I don't have the T. The M is 50. Thank goodness it's in kilograms. And the velocity here is 8 for the difference. Remember, it's triangle V. I'm going to go ahead and 40 cancel, 40, the amount of T in seconds. Not bad. Easy cheesy. Well, believe it or not, that this whole purpose, momentum, some people, they do this for a job. Some engineers are thinking about the conservation of momentum and it's like a whole profession out there. It says the conservation of momentum. If momentum is conserved, which means it does not change, because it's conserved, it stays the same. How could someone decrease the force at which they are going to be hit in a collision? Kind of like, what if you're roller skating or skateboarding and you fall off? You're about to fall and hit the ground. How can I decrease the amount of force that's going to happen to me? Well, we just talked about it, right? If we increase that time, or by increasing the amount of time to come to a complete stop, we can then decrease the force. All right? We can then decrease the force. And like I said, some people, this is their job. They're thinking about momentum. Momentum's going to be there. But how can I decrease the force, and especially on actual people, right? The last thing you want is to go through 4 concussions in your high school and elementary football years. So how are you when you're in college or afterwards? How's your thinking capacity? How is your long-term memory? Oh my goodness, right?